Okay. First of all, let's recall the situation so far, what we have done. You have a set A of cardinality 3.18p, and this, I have this model, and from this set A we got a half circle having m points, and these m points do not lie in the half circle, they lie in a proper part of length L, which is around 0.444 when m is equal to 0.238. That's where it lies. And then we want to say, given this situation, we want to say that it is untenable. I mean, therefore the whole thing has to be there. And in order to do that, what we were thinking of was the so-called exclusion zone. That is, the presence of one element will already exclude the presence of many other elements, and because that, etc. Oh, before that, let me say, therefore I will only talk about this one case, 0.238 for example. Okay, the other cases are sort of similar. That is essentially because in the last 10-15 minutes, I want to devote on the construction by Saska to have a set A of 0.25p, which is Sumfree, but which is not a dilation of mod A to p minus A. And in fact, so this way suggested that I should start with that example. But you know, it seems that this paper has not been published, it is only in his thesis. And consequently, I thought I should probably get his permission before talking about that. And I got the permission just half an hour back. He sent me an email saying that, okay, I can talk on this. Okay, and therefore that will be therefore for the last 10 minutes, and therefore I will. Yeah. Yes. Okay, now this is the situation, and what we wanted to do was so-called exclusion zones, which therefore let us assume that A is, I called B, but since I am more accustomed to calling it A, this A will be a general set. A will be contained in 0 to L. And I am also assuming that 0 and L belong to A. Then under these conditions, A minus A is large, is what we want to do. I knew what large is, but anyway, yeah. If L is lesser or equal to 2m minus 2, which is really the case for us, L minus m plus 1 divided by k and m over k is contained in A minus A. Good. When I have the spectacle, why am I not through English and finding it very difficult to read what I have written? And therefore that is an exclusion zone. And also, if L plus 1 is lesser or equal to 2k minus k, 2k minus 1 divided by k into m, then minus m over k minus 1 to m over k minus 1 is an exclusion zone. And we also verified yesterday that for k is equal to 3, this condition is satisfied. And for k is equal to 2, it is not satisfied. And that was a comment which he was making, that in the original paper of Love, somehow it looks like, at least for the integers and not for z over pz, one can even take k equal to 2 and say that minus m to m is an exclusion zone. Since I didn't have much time to verify that particular statement, I will not make more comment on that. Yeah?
inside the integers and then inside the sums that afterwards by the isomorphs.
Sorry? Two isomorphs.
After the Feynman isomorph.
Yeah, I see. After Feynman isomorphism, I see. Okay, that I have to just check and then I will come. And then we also had another result which says that if you define your lambda to be 2m minus L minus 2, and if you have some u to u plus L, A is contained in u to u plus L, then, and if there is an A which lies between L by 4 and L by 2, then 2a minus lambda to 2a plus lambda is also an exclusion zone. Therefore, we have so many exclusion zones. And what we want to do is to have one more exclusion zone. Okay? Now you see, from this particular information, and we have also defined, now taking a different model, at different times I will take a different model. Taking this different model, we defined the mu to be the maximum of mod z, minimum of mod z with z belonging to A. That is a minimal element of z. First of all, there is a minimal element essentially because you see the neighborhood of 0 is an exclusion zone. Taking k equal to 3, you see minus m by 2 to m by 2 is an exclusion zone. And therefore, there is a neighborhood of 0 which is an exclusion zone. Since there is a neighborhood of 0 which is an exclusion zone, I can define what is a minimal number, and the minimal number is what I am calling mu. And therefore, this information with the k equal to 3 will give you mu bigger than or equal to m by 2. And for small enough m, this is not a good lower bound. For a small enough m, we can improve it. Therefore, let us say m equal to 0.238 or something like that. That's probably the worst case in some sense, because if there are more and more elements already in that half circle, then it is much easier to prove that the rest of them are only in the half circle. Therefore, the worst case would be when m is very small, 0.238, only those many elements are in the half circle. Okay, in this case, how do you do that? Therefore, in this case, I claim that one can improve, that's a claim, that one can improve mu to be bigger than or equal to 0.158, which would be bigger than m over 2, given the fact that m is equal to 0.238. Since m is 0.238, m over 2 will be only 0.119, and this is what I want to claim. How do we prove that? Remember, mu belongs to A. Mu is a minimal element and mu belongs to A. And now consequently, A intersection A plus mu is empty. Good. And now you can define your B to be A union A plus mu. Okay. And now I can apply the Lewis theorem for this B. The Lewis theorem says that an half interval with the rotation of A contains at least cardinality of A divided by 2 plus P over 2 pi arc sine cardinality of A hat 1 sine pi over P elements and I can apply that theorem to B now. Okay? To start with, therefore, any half circle will contain, in B, this case, mod B over 2, applying this, plus P over 2 pi, arc sine P hat 1 sin pi by p elements. Therefore, any half circle will have at least those many elements. But on the other hand, you have assumed that A has only m elements on any half circle. Since A has only m elements on an half circle, A union A plus mu can have only 2m elements on an half circle. It cannot contain more than 2m elements. And that consequently, therefore this is bigger than this, and therefore this should be less than or equal to 2m. Correct. Because any half circle can contain only 2m elements. Good. But now on the other hand, we can look at what do we know about the B hat 1. Now the B hat 1 is nothing but a exponential e power 2 pi I a over p plus summation e power 2 pi I a plus mu over p. And then you can take an a power 2 pi a over p common, which is a hat 1 into 1 plus e power 2 pi I mu by p. And now you can therefore look at this absolute value, which is 2 times a hat 1 into cosine pi mu by p. And therefore you can now put here a hat 1, which about which you already have any information, into cosine pi mu by p. Okay? This first of all implies that mu cannot be 0 and things like that, because if mu is 0, cosine pi mu by p is 1, and therefore R sign will be much bigger, and therefore this equality cannot hold. Particularly if m is small, that already forces your cos 2 pi mu by p to be small, which will force your mu to be big, and if you do the calculation, then you get mu is bigger than 0.158, which we claimed. Okay, therefore that is an exclusion zone. Therefore, up to mu there are no elements of A. Okay? That is the situation we are in now. Yeah, now I need these things. The mu part I can forget. So far so good. Now let's take a model, a different model. Now we take a different model. That's a model which I am now taking. Okay, in this model, what do we know? We know that k equal to 2, therefore minus m by 2 to plus m by 2 belongs to a minus a. And also, this tells you that L minus m minus 1 by k, m over k is not in a minus a, I can take k equal to 1. Therefore, L minus m minus 1 to m does not have any element. And the same thing is negatively true. Therefore, now we have not so many elements, and now you have this element, let's call A1 plus, and this we will call A2 plus, and the corresponding thing, this we will call A1 minus, and this we will call A2 minus. And then there are elements between P by 4 to 3P by 4. And that being a half circle contains at most m elements. Okay, this is the situation now. Okay, now once I have this situation, then I can prove the following, that the A1 plus, for definiteness, let me assume that A1 plus is bigger than or equal to A1 minus, which I can always do. Okay? And now now the next lemma which I want to prove is A1 plus is non-empty. All these statements are actually easily proved if you just look at an appropriate model. Therefore, let me prove that A1 plus is non-empty, and therefore let me do that, and then let me take another model which would give you the proof immediately. And the negative of that. And then translate whatever information I have. The information is 0 to m by 2, there is a no. M by 2 to L minus m minus 1 is what is called A1 plus. And suppose A1 plus is empty, then this is also a no. And L minus m plus 1 to m is already a no. All of them are no. That essentially means that mu is bigger than or equal to m. But m one can easily check to be bigger than or equal to p minus n plus 1 over 3. And yesterday we verified that if mu is bigger than p minus n plus 1 over 3, then already we are through. Then mu is bigger than n itself. And therefore that proves the result. Okay? And the next thing is, essentially I can even improve the estimate for L. You see, I have already proved somewhere, which I have not written, that this L is less than or equal to p minus n minus m minus m, which followed from the fact that a minus a is bigger than or equal to L plus m. And one can actually prove a little more, and which is probably needed on those cases which I am not going to discuss, only for m, but in any case, I think to complete the proof I should give that. That's the next lemma. L is in fact not only less than p minus n minus m, but p minus n minus m into 2 times a1 plus 2. And okay, therefore let's prove how to prove that. Now look at the following sets, A2 plus plus A2 plus, and then A1 plus plus A1 plus, and then A0 minus A0, and then A. These are the things which I am looking to get. 1 minute. No, A2 plus, no, sorry. That's what I thought. A2 I should get, no, A2 minus minus A2 minus. And I leave it to you for an exercise. See which is the interval in which A2 plus A2 plus lies. Look at the interval where A2 minus plus A2 minus lies. Look at the interval where A0 minus A0 lies. And look at the interval where A lies. And then you prove that all these elements are disjoint. Therefore, all these sets are disjoint. Therefore, their cardinality added together can be at most P, because I have 4 disjoint sets in 0 to P. Since I have 4 disjoint sets in 0 to P, their cardinality. Therefore, I should know just what is their cardinality. A2 plus A2 plus, you see A2 plus is within a half circle. And once something is within a half circle, then by a 2 isomorphism, you can as well do it as over integers. It doesn't really matter. Okay, because you can always do the things. And therefore, this cardinality is at least 2A2 plus 1. Because for the integers, minus 1. For the integers, it is true. A plus A is bigger than or equal to 2 times cardinality of A minus 1. And similarly, here it is 2 times A2 minus 1. And A0 minus A0 we have already seen to be bigger than or equal to minimum of L plus M into 3M minus 3. And we proved that the 3M minus 3 cannot hold, therefore it has to be L minus M. And this has to be N. And their sum is less than or equal to P. And that proves the result. Okay? Now we are almost there. Now I just need one more exclusion zone. With one more exclusion zone, I would be perfectly okay. Therefore, let me write one more exclusion zone. Let J plus be equal to A1 plus A1 plus an interval I, where I is minus lambda to plus lambda, where lambda has been defined here. Okay, I have defined the lambda there, and this is A1 plus A1 plus lambda. And now you see, for any such A1 plus, then this A, which lies between L by 4 and L by 2, then 2A minus lambda to 2A plus lambda is a exclusion zone. Therefore, from that you can conclude 2A plus lambda plus 2, therefore from this you can conclude that this J plus is an exclusion zone. And the cardinality of J plus is also you know. And the cardinality of J plus is this A1 plus A1 plus has 2 A1 plus minus 1 elements. And if you have a set of that and you add with an interval, then just the interval gets added up. And therefore this has essentially 2 times A1 plus minus 1 plus 2 lambda elements. And this is, and what is more important is that one can again define from this J1 plus, that this J1 plus lies between lambda plus 2 comma L. And the same thing for J1 minus, which would be contained in the negative part of that. Okay. Therefore, we have got one more exclusion zone, which is J1 plus. And J1 plus is excluded, and it has a cardinality which is 2 times mod A1 plus minus 1 plus 2 lambda. And now more or less the proof is over, and therefore just let's now write the proof. From here we have done that, okay, we have one remark from this, which is what I need. Outside P by 4 to 3 by 4, the elements are A1 plus, union A2 plus, union A1 minus, union A2 minus. These are the only elements outside P by 4 to 3 by 4, which is what I want to use. And now I am going to do the last step, okay, which is also a sort of an exercise, but therefore let me just write what is the last step. And for the last step, of course, I have to going to take a still different model, and that will prove the last step. I'm just taking the model from minus lambda to p minus lambda. I can take any model if you want. And I want to know how many elements of A can be there. Break this into two parts. I will check how many elements of A can be there in I1. And then I will check how many elements of A can be there in I2. And then I will check whether that add up to n at all, 0.318. Okay. Now let's see how many elements are there in I1. This I1, remember, is, okay, first of all, let me make the statements clearly. I don't need now any of them. So, what? Most important thing I forgot. Anyway, I1 is outside P by 4, 3P by 4. Because P by 4, 3P by 4 is included in the I2, and therefore I1 is P by 4 to 3P by 4. And once, but we have already seen that outside I1, the only elements possible are A1 plus union A2 plus union A1 minus union A2 minus. And therefore, consequently, the elements which can be here are only A1 plus, union A1 minus, union A2 plus, union A2 minus. Only those many elements are possible. Okay? And now I want to know how many elements are possible in this lambda to P minus lambda. In this lambda to P minus lambda, the length of the interval is P minus 2 lambda. Therefore, the maximum number of possible elements is only P minus 2 lambda. Good. However, both your J1 plus and J1 minus are contained in I2. Okay, J1 plus is lambda 2 to L, and J1 minus is P minus L to P minus lambda by 2, and therefore your J1 plus and J2 minus are contained in those, and they are exclusion zone. Therefore, they cannot contain. Therefore, the maximum number of possibilities for here is the length of the interval minus the cardinality of J1 plus minus cardinality of J1 minus. That's all possible there. Once that's all possible, therefore the total number, you know what is possible. And then I leave it to you to just a simple exercise to add all those things and to prove that this number is strictly less than n. Therefore, all the elements cannot be there. And that proves the case 0.238. And the same proof works more or less up to 0.244. And from 244, you have to use exactly similar argument. Look at the exclusion zone, throw away the exclusion zone, look at the interval, and so on. Good. And that proves whatever I wanted to say about the Somfree. Is it okay? I mean, just the idea is that there are a lot of exclusion zones. You look at all the exclusion zones and throw away them and just look the length of the interval. And first you say that there is a half circle containing a lot of points, and that point itself is inside a L, and then you keep on doing the exclusion zone business. And therefore all our new ideas are essentially trying to get little more exclusion zones and also to do something on the Fourier. On the Fourier, what do we want to do? That there was a negative sign in summation mod a hat t whole square times a hat t equal to minus something, which I just used as summation mod a hat t whole cubed is bigger than or equal to something. But there I am losing a lot, and that is something which one can do there. Good. This completes the first part of my lecture, and the last part we have to just look at an example where it is not really to construct a set of cardinality p by 4 essentially such that no dilation would lie between mod a to p minus mod a. You see, this middle one-third for generally means this precisely this. Middle one-third precisely means that I am looking at this interval mod a to p minus mod a, and I would like to know whether that lies there. Okay? Therefore, now again this thing also is somewhat lot of easy, laborious calculations, and therefore most of them I leave it as an exercise. I will just give the construction. Therefore, that's a construction. Yeah. Fix a prime P congruent to 5 modulo 8 and define your M to be P minus 1 divided by 4, therefore roughly P over 4, and K which is M minus 1 over 2 which is P minus 5 divided by 8, and fix a B which lies between K by 2 and P by 3 minus M. Okay, now let me again draw the graph. Take this model. And this K is around P over 8, and therefore K by 2 is around P over 16, and therefore your B lies there. That's a P over 16. And there is a P over 3 minus M, which is P over 12. And you have a B sitting there. You choose any B there. which essentially lies between p over 16 and p over 12. Therefore, I'm not going to give only one construction, lot of constructions. And then your k is there, which is around p over 8. You take all elements between b and k. You take all elements between b and k, which you call I1. And then you have an m, which is around p by 4. And you have an m plus b minus 1. And you take all elements here. This is I2. Therefore, let me just define I1 is equal to b plus 1 up to k. And I2, which is m plus 1, etc. up to m plus b minus 1. If you want, it's better to write I1 plus and I2 plus. And I1 minus is the negative of I1. And I2 minus is the negative of I2. And the A which I am going to take is I1 plus union I2 plus union I1 minus union I2 minus. Now let's see how many elements it has. I2 has around b elements and I1 has around k minus b elements. Therefore, I1 union I1 plus has around k minus b. Therefore, the positive part already has around k elements and the negative part has around k elements. Therefore, there are around 2k elements and 2k elements is precisely p by 4. Okay? Therefore, there is a k minus b elements here, b elements here. Therefore, totally there are k elements, k minus b and then b, the totally k elements. And then the negative part also, 2k elements. Now I have to prove various things. First of all, I have to prove that this is Sumfree, which I will leave it as an exercise after a hint. And then I have to prove that there is no dilation which will put you between A and B minus A. To prove Sumfree, we are not even going to look at the elements. Just to look at the intervals in which I1 plus I1 plus, I1 plus, minus I1 minus, all the possibilities lie. Even the intervals where they lie is disjoint from the intervals where A lies. Therefore, we are not even look at the elements of whether these two are plus equal to that another element, etc. I mean, their support is already disjoint. Okay? That is, for example, if I now take this I1 plus plus I1 plus, for a simple example, I1 plus by I1 plus will lie between 2b and 2k. And the 2k, by definition, is p minus 5 by 4. And that is less than m, which is p minus 1 by 4. Therefore, this 2k is less than m, and therefore this interval will not come and intersect here. And that's exactly what we are going to do for every such intervals. I1 plus I1, we are going to do it. I1 plus I2, for everything we can do it. And therefore it is easy to prove that it is Sumfree. And now I have to prove that no dilation lies there. Okay? Now why is this no dilation lies there? First of all, you use the way I have defined A is equal to minus A. Because I have taken something and then it's negative, union negative also. Good. And therefore, if for any D, D times A is equal to minus D times A. Therefore, the dilation by D and the dilation by minus D are the same. And if the dilation in D and dilation in minus D are the same, which means essentially I can assume one less than or equal to D less than or equal to P minus 1 over 2. Correct? No, what I am saying is A by construction A equal to minus A, because I have taken something on the positive side and its corresponding negative part. And therefore A equal to minus A. Therefore D times A equal to minus D times A. Good? Minus D is the same as P minus D. Okay? It doesn't really matter, you are in ZP star. Therefore the dilation by D and the dilation by P minus D are the same. Since the dilation by D and P minus D are the same, we can as well assume my D lies between 1 and P minus 1 over 2. Because if my D is much bigger than that, I can take the P minus D, which will come between 1 and P minus 1 over 2. Therefore, I have to only look at the dilation between 1 and P minus 1 over 2. I need not do further. Good? And now I will prove it as an exercise, leave it as an exercise that, okay, for D less or equal to 8. You can just simply verify what happens for D less or equal to 8. Therefore, I have to only bother about what happens when D is bigger than or equal to 9. When D is bigger than or equal to 9, if I now take the D times A, and the D times A will not be, therefore what is that I have to prove? I have to prove that D times A will not be sitting inside cardinality of A and P minus cardinality of A. That's all what I have to prove. Okay? And in fact, I am not even going to take the A at all. I am only going to look at the I2 plus. And then I am going to prove that. I am going to prove that D times I2 plus itself cannot be sitting between cardinality of A and P minus cardinality of A. I am not even going to bother about the other elements of A. I am only going to concentrate only on I2 plus. Okay? Therefore, what we should do? I should do every element here, multiply by D and see where it lands. And then I would like to know whether it lands in this interval. Correct? That's exactly what I am going to do, which means I am going to plot. What I am going to do is I am going to plot D times M first. I take that M, multiply by D, and then take the next element, multiply by D, and then take the next element, multiply by D. Keep doing that. If I take each element by element, multiply by D and plot, okay? But then after some times, of course it will exceed this interval. Once it exceeds this interval, it will come back to the front. Correct? Because every time I am taking mod P. Since I am taking mod P, once it crosses the interval, it will come back original. Is it okay? Oh, now I am taking this model. I am taking this model and now plotting D times M plus 1, D times M plus 2, etc. Once it crosses, then it comes back. Is it okay? Good. Therefore, when I keep plotting, okay, there are two types of moves. The first move, D towards In this direction, it goes by a length d. That's what happens. Otherwise, there's a second move. It goes a length d in this direction and then comes back a length p in this direction. Because once it crosses, it comes back by a p. Therefore, it either goes by a length d and stops there, or it goes by a length d and comes back by a different distance p. Is it clear? That's exactly what it does. When I take m, m plus 1, m plus 2, etc., multiply by d, reduce modulo p, and then see what happens, the movement is clear. When I take the d, m plus 1, m plus 2, etc., when I multiply by d, every time it moves, jumps by a distance d, and sometimes afterwards it comes back, etc. Now I prove the lemma. First, if d is bigger than or equal to 9, there is a move 2. It cannot be only move 1. There is a move 2. Therefore, it cannot be only jumping d, etc. There is some time when it has to move d and then come back by p. A move 2 has to be there. Okay, the reason is obvious. I have this interval of length b, and then when I am plotting, and suppose it goes only by distance of d, and doesn't come back at all, and if therefore if all the elements come here, then there are b elements, each with a distance d in this interval. Therefore, this length of the interval has to be bigger than d times b. Because if the length of the interval is not bigger than d times b, then all of them cannot be here. Therefore, sometimes people, and that means what? P minus cardinality of 2 times cardinality of A is bigger than or equal to d times b. And that is simply not possible because your b is at least k over 2, which is p over 16. No, k over 2, which is p over 16. And b is k over 16 and d is your 9. And this length of this interval is cardinality of A is around p over 4. 2 times cardinality of A is around p over 2. P minus 2 times cardinality of A over, therefore it's around p times 2. And that is not possible. That's simply not possible because d is bigger than 9 and b is bigger than p over 8 and over that p over 16 and over that. That's exactly the reason why I wanted you to do d up to 8 as an exercise. Okay? Because up to d equal to 8, it can be just only the forward move 1 and there is nothing else. Good. Therefore, that is not the case. Therefore, there is at least one move 2. Now I want to know what happens just at that stage when there is a move 2. I want to see what happens at that stage where there is a move 2. Therefore, I have here, I have a cardinality of A, I have cardinality of P, this is P minus A, here, and I am here. That's, I am keeping on writing dm plus 1, dm plus 2, etc. I have come up to x, and at this particular stage there will be a move 2, which means it will go up by a d and come back by a distance p. Okay, this is the last stage, which means that once it has a distance of d, it goes outside the interval. Because otherwise it will be only move 1. If it lies inside the interval, it will be move 1. It just goes by the d. Move 2 means it has to go outside the d and comes up by everything. And therefore, when it goes up, it goes here, outside the interval, and then comes back. And the claim which I want to make is, when it comes back, it is still to the left of this. When it comes back, it is still to the left of this, and consequently, it won't be in that interval cardinality of A to P minus cardinality of J. Is it okay? Therefore, at that time, when it makes move 2, when it goes up by a D and comes back by a P, still it cannot go inside this interval. it still will be left. That's all what I have to prove. Okay, and that I think is more or less clear, because what is x plus d minus p? That is less or equal to your x is p minus cardinality of A, and d is p minus 1 over 2 minus p, and then I want to say that this is less than cardinality of A. Okay, and that essentially means that I have to prove that p minus 1 over 2 is less than 2 times cardinality of A. But what is the cardinality of A? This number has exact, though I have to bother about the O of 1. This number has k minus b plus 1 elements, and this number has b elements, and then that gets multiplied by 2. Therefore, the cardinality of A is 2 into k plus 1. And 2 into k plus 1 is what? Therefore, this is cardinality of A is 2 times cardinality of A is k plus 1, and k plus 1 is p plus 3 by 8. No. So cardinality of A is 2 times k plus 1, which is p by 4, and sorry?
You multiply 2, A is twice that part, and you multiply by 2.
Oh, yes, that's a cardinality. Okay, sorry. And that is true, and therefore this is true, which means that in the second move it goes there and comes back, it is still to the left of A, it would not have entered the interval, therefore I have produced one element which is outside this interval, and consequently there is no dilation which lies in this interval, cardinality of A to p minus cardinality of A. Okay? I think with that, I told you I will stop at what, 10 minutes earlier? I have stopped only 7 minutes earlier. That's okay. That's all. And that's my last. Thank you.